Integration by parts. In this video, we're going to develop a technique that will help us evaluate a wide variety of integrals that we couldn't integrate before. So to do this, let's start by letting f and g be differentiable functions. Then by the product rule, we know that the derivative of f times g is equal to f times the derivative of g plus g times the derivative of f. So now, if we take this equation and integrate both sides, we come up with this equation. Now if you look at this equation, on the left-hand side, this right here, I'm taking the antiderivative of the derivative of f times g. Well, that's just equal to f times g plus some arbitrary constant. So now if we take this equation here and solve it for the first term on the right-hand side, we get this new equation, which says that the integral of f times g prime is equal to f times g minus the integral of g times f prime. And there's this arbitrary constant here, but we don't need to worry about it. We can get rid of it because when we do this indefinite integral here, we're going to end up with another arbitrary constant. So this equation becomes this one. And this is how we could say, if I could see an integral that says that I can recognize as the integral of a function times the derivative of another function, then I know it's going to be equal to the function times the second function minus my second function times the derivative of my first function. So this is often rewritten by letting u be equal to f, v be equal to g, and getting this equation that the integral of u dv is equal to dv minus the integral of v du. And this is what we call integration by parts. Now, you can also do integration by parts for definite integrals. When you do that, you just need to make sure you evaluate properly. So if your definite integral goes from a to b here, you're going to evaluate uv from a to b. And then this integral here, your limits of integration stay the same as a to b. So let's do an example to see how this is going to work. Let's evaluate the integral of x times e to the x. So what we need to do is we need to recognize this integral in the form the integral of u times dv. All right? And one way we can do this is we can let u be equal to x and dv be equal to e to the x dx. Now, when we do that, now I can figure out what du is by taking the derivative. So I get that du is equal to dx, and I can figure out what v is equal to because v is equal to the antiderivative of e to the x dx, and we know what that is. It's equal to e to the x. So what we end up with is this integral is equal to uv minus the integral of v du. We plug in our values for u, v, and du to get that this integral is now equal to x times e to the x minus the integral of e to the x dx. And we know what that is, so we get our answer that the integral of x e to the x dx is equal to x e to the x minus e to the x plus c. All right, so before we go on, let's take a look at this example. Notice up here, when I calculated the antiderivative of dv and I got v is equal to x, I didn't put down the plus c for the arbitrary constant. And the reason why we don't need to put it here is that it would have eventually canceled out somewhere along the way. So when you're doing your integration by parts, you don't need to put the plus c here with your v. All right. So let's try another example. Let's evaluate the integral of x squared times e to the minus x dx. So this looks very similar to the problem we did in exercise 1. So let's try doing that in the same way. We need to make some choice for u and dv. So let's let u be equal to x squared and dv be equal to e to the minus x dx. Once we do that, I know what du is. I take the derivative. I know what v is because I know the antiderivative of e to the negative x is negative e to the negative x. So I now know that my integral is equal to uv minus the integral of v du. I plug everything in. And now we're going to take this, after we've plugged all our values in, and simplify it a little bit. Take care of these parentheses here and the negative signs. To end up with it's equal to negative x squared e to the minus x plus 2 the integral of x e to the minus x. Alright, so now to integrate this integral right here, we're going to need to use integration by parts again. And again, this is very similar to example 1. We will choose u to be equal to x, dv to be equal to e to the minus x dx, and then we go ahead and find du and v. We say, okay, what we're trying to find is equal to this. I plug in my values for u, v, and du to get this equation here. So now this, if we just simplify it a little bit, is equal to this. And now the only integral I have left is 2 times the integral of e to the negative x dx. We know how to find that antiderivative. We go ahead, and then we just simplify our answer. I'm going to get rid of these parentheses here by rewriting the plus as a negative. And then I have a negative on each of the terms here, and an e to the minus x on each of these terms. I'm going to factor it out to get my final answer. Alright, so in example 3, we're going to look at a very important integral. Let's look at the integral of natural log of x dx. Now we don't know any function right now when we take its derivative that we end up with the natural log of x. So we haven't been able to find this antiderivative. But now with integration by parts we're going to be able to. So here's how we're going to do it. The first thing we're going to do is choose our u and our dv. So let's let u be equal to the natural log of x and dv be equal to dx. When I do that, I find that du is equal to 1 over x dx and v is equal to x. So writing this integral of natural log of x in the form uv minus the integral of v du, we get that it's equal to the natural log of x times x minus the integral of x times 1 over x dx. And if we simplify our integral, we get that this is equal to x, the natural log of x, minus the integral of dx. So we end up with that the integral of the natural log of x dx is equal to x, the natural log of x, minus x plus some arbitrary constant. Alright, our next example is going to show us how integration by parts can be used to integrate an inverse trig function. So here, let's evaluate the definite integral from 0 to 1 of tangent inverse of x. So what we're going to do is we need to make our choices for u and dv. So let's let u be equal to tangent inverse of x, because I know how to find its derivative. And let's let dv be equal to dx, because I can find its antiderivative. So the derivative of u is du, which is equal to 1 over 1 plus x squared dx, and v is going to be equal to x. We go ahead and plug our information into the formula for integration by parts to get this equation here, that it's equal to tangent inverse of x times x evaluated from 0 to 1 minus the definite integral from 0 to 1 of x times 1 over 1 plus x squared dx. And then if we take the first part and evaluate that, we get this part right here. And then if I simplify the integral, it comes out to this. And now we need to simplify this a little bit. I know that tangent inverse of 1 is equal to pi over 4, and tangent inverse of 0 is equal to 0. So I get that that is equal to this, which when you simplify it down gives you pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. Alright, so now we just need to find the value of this integral. And to do that, we're going to use a u substitution. Let's let u be equal to 1 plus x squared. That tells us that du is equal to 2x dx. So here's my x and my dx. Let's get rid of the 2 by dividing both sides by 2. And then, since it's a definite integral, we have to change our limits of integration. So when x is equal to 1, u is going to be equal to 2. And when x is equal to 0, u is going to be equal to 1. So that gives us our equation is going to be equal to the integral from 1 to 2 here, 1 over u times 1/2 du. We know how to evaluate that. We just go ahead and say, okay, the integral of 1 over u is the natural log of u. We evaluate it from 1 to 2. When you do this, make sure you put your parentheses here because that negative sign's on the whole thing to give us this. And now to simplify, here what I'm going to do is this 1/2 by my property of the logarithms, I can bring it inside and make it the exponent of the 2 here. And here the natural log of 1 is 0. And then our final answer will be pi over 4 minus the natural log of the square root of 2. All right. Let's look at one final example, and it's pretty interesting. Let's evaluate the integral of e to the x times cosine x dx. So the first thing we do is make our choices for u and dv, and let's let u be equal to the e to the x, and dv be equal to the cosine x dx. When we do that, we go ahead and evaluate du and v, and that gives us that the integral of e to the x cosine x is equal to e to the x sine x minus the integral of sine x e to the x dx. Alright, since the integral of e to the x sine x dx is similar to our original integral, it seems that nothing has been accomplished. But let's go ahead and integrate this new integral by parts. To do that, we'll go ahead and let u be equal to e to the x and dv be equal to sine x. That tells us that du is equal to e to the x dx and v is equal to minus cosine x dx. We go ahead and put those in to our formula here to get that the integral of e to the x cosine x dx is equal to e to the x sine x minus, all in big parentheses, e to the x times negative cosine x minus the integral of negative cosine x e to the x dx. If we simplify this out, this is the integral we end up with. Now, look at that integral again. It said the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. Well, that's the same as this side over here. So it seems like we're going around in circles, but really we're not. What we can do is, since these two terms are the same, let's take it from the right-hand side and move it over to the left-hand side. And now if we divide both sides of the equation by 2, we have found the value of the integral we were worried about. We get that the integral from e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x, all divided by 2, and then plus c.